Hello everyone, our paper topic is ADOPS, an anomaly detection pipeline in structured logs. Anomaly detection aims to identify behaviors that do not conform to expectations. Most existing methods focus on the improvement of anomaly detection accuracy. However, in real-world applications, especially in industrial scenarios where hundreds or thousands of projects may need to be monitored for anomalies, training an anomaly detection model for each project and deploying it online is difficult to achieve. Our focus is on building an efficient, stable, and general anomaly detection pipeline to accelerate the development of anomaly detection tasks. We construct a pipeline of log anomaly detection named ADOPS to provide efficient and diverse anomaly detection services. It enables to 1. Accept JSON format for establishing or modifying anomaly monitoring tasks, 2. Execute multiple anomaly detection methods, 3. Recommend appropriate anomaly detection thresholds for users. 4. Support offline analysis of logs, but also anomaly detection on the data stream. Next, we describe the overall architecture of ADOPS. ADOPS comprises three main components: the pre-computation engine, the feature store database, and the intelligent detection engine. The pre-computing engine aims to recommend anomaly thresholds to novice users who need help setting them. We employ Apache Kylin as the pre-computation engine to measure potential monitoring items using player ID and time as dimensions. After the user provides monitoring information, the pre-computing engine recommends appropriate thresholds for them. Then, the pre-computation engine passes the configuration information to the intelligent detection engine to create a real-time task. Feature Store Database is a data management tool for machine learning. It stores feature values and endorses sharing feature values across teams and domains. FSDB is the data provider for intelligent detection engines. In FSDB, all feature processing relies on SIRQL statements. Engineers can use SIRQL statements to turn offline data into features for model training. Then it could switch the SIRQL feature processing statement from offline to online mode and deploy online. The intelligent detection engine is responsible for managing online tasks and improving the efficiency of model development. It receives the monitoring configuration from the pre-computation engine and creates Dask real-time monitoring tasks based on the configuration items. After the engineer completes the model training, he can provide data format, model storage location, and model type to the intelligent detection engine in the form of JSON, and the intelligent detection engine can deploy the model online to provide real-time anomaly detection services. Finally, let's demonstrate how to use ADOPS. Our demonstration consists of two parts. We will show how users quickly build multiple real-time anomaly detection tasks without requiring programming. We will also show how users can simplify the development and deployment of complex anomaly detection models through ADOPS. First, let's go over how to start the ADOPS pipeline. We start by getting the local IP address and setting environment variables. Then, we start the Kylin and MySQL containers with the Docker Compose command. Now the Kylin and MySQL containers are up. Since the image build of ADOPS takes some time, we have built it in advance. These are the ADOPS image build and container start commands. At this point, all services of ADOPS have been started. To use the anomaly threshold recommendation feature of ADOPS, we need to pre-calculate the data using Kylin, which supports Hive as the data source, or upload the data via CSV file. We need to build the model and cube based on the fact table and complete the data pre-computation. The detailed construction process can be found on the Qilin website. This is the result after pre-computation. Next, we introduce the whole process of anomaly detection using ADOPS. We first introduced how to complete the creation of anomaly detection tasks and online monitoring without programming. We can use the API interface to view cube information, including the start and end time of the cube, dimensions and measures, the data types of the specified columns and candidate values. Next, we get the recommended thresholds from the pre-computation engine. Like in this example, we set the monitoring time to 10 minutes, the filter condition to circ type equal to 14, and the monitoring item to delta, and get the recommended thresholds to 5297. And then we save the monitoring configuration in the database. We can also view all the monitoring configurations in the database as well as the specific configurations for a given ID. And we can also modify the configuration for a given ID as well as delete the configuration for a given ID. Finally, we bring the monitoring task online through the intelligent detection engine. We can see the monitoring configuration in the database with the live tasks. Next, we introduce how to develop complex anomaly detection models through ADOPS and deploy them online. Due to time constraints, we have completed the data processing and model training process beforehand. We first connect to the feature repository. Then create a database in FSDB and create tables. Set Circle to development mode during model training. Load data from the file into the table. This is the raw data in the table. Then we develop the data processing circle to convert the raw data into features and export the features. Next, we adopt these features to train the model XGBoost and get 99% accuracy. Note that we need to save the model to a file. We then set up Circle as an online mode and deploy it online. At this point, the data can be converted to features by calling the interface. Next, we need to save the model configuration to the database. We need to provide the FSDB port, model storage address, model type, database name, Circle deployment name, schema information of the data with the port where we plan to deploy the model. We can also get and modify the model configuration by ID. Next, we bring the model online with one click through the model deployment interface. The model is now online. We check the deployment effect based on the model deployment port. Based on the test data provided, the inference result is 0, which means test data is not fraud. After that, let's explore the real-time data processing capabilities of ADOPS. First, we generate real-time data. We start Kafka and create two topics. Then we generate 10 data and send them to the specified topic. We monitor the task online through the monitor interface. At this time, ADOPS will read the real-time data, and based on the model to reason whether there is fraud. From the database, we can see that there is no fraud data generated at this time, and the deployment of the model and monitoring tasks have been written into the database. Next, we generate some anomaly data. After the anomaly data is sent, you can see that the anomaly data has been detected by ADOPS and stored in the database. Finally, we demonstrate how to perform anomaly attribution with ADOPS, which has an internal integrated SHAP library that shows the impact of different features on the predicted results of the model. It supports exploring the impact of feature values on predicted values on a single piece of data. We can also use it to look at the impact of features as a whole on the predictive results of the model to find the cause of anomalies.